Today I will be presented by Tom Kaiser, who is the President and Chief Operating Officer of Terra Green Energy, which is based in Smethport, Pennsylvania. He and his partners have been working on torrefaction for almost 7 years now. Tom has a bachelor's degree in the physical sciences from the University of Pittsburgh on the Bradford campus and an MBA from St. Bonaventure University in Allegheny, New York. After serving 4 years in the United States Marine Corps, the majority of his career was spent with the Quaker State and Astro corporations, where he served in various technical and management positions, including Quality Control Manager, Director of Quality, Refinery Manager, VP of Refining, and VP and General Manager. After leaving these positions, he was elected and served as chairman of the McKean County Board of Commissioners before helping found Terra Green Energy. As will be seen in his presentation, he's always had a strong interest in economic development, having once served as a president of a local economic development corporation. Born and raised on his grandfather's dairy farm in McKean County, he has a lifelong interest in agriculture, forestry, and renewable energy that informs his work today. And we are very much looking forward to hearing more about it. So Tom, the floor is all yours.
Thank you very much, Sarah. I'd like to thank you and other members of the new bio team for the opportunity to talk about our company and torrefaction today. And I will proceed. I have a lot of good information here today, and I hope everyone finds it as interesting as I do. The topics that we're going to talk about today, there's, again, quite a bit of information, but give us an introduction to Terra Green. We'll talk about what torrefaction is, the characteristics of torrefied wood versus other forms of wood, issues solved by the use of torrefied wood. I'm going to talk about on the national scene what's happening with the consortium of advanced wood to energy systems, CAUSE, that's just been formed this few months ago. We'll talk about different supply chain models. We'll go back and talk about Terra Green's torrefaction technology and our small-scale commercial torrefaction facility that we have constructed. We will talk about the International Energy Agency's conference on co-firing that occurred a couple of months ago and that we were lucky enough to participate in. The economics of co-firing with torrefied biomass, the environmental benefits, the economic beneficiaries, and finally some final remarks. So I will proceed. Terra Green Energy is a renewable fuels technology development company specifically focused on the development of a biomass pretreatment technology known as torrefaction. Our chairman is Mr. Harry Halloran, Jr. Mr. Harvey Galjubek is our CEO, and I'm the President and Chief Operating Officer. Mr. Halloran owns ARB, and ARB is the majority owner of Terra Green Energy. ARB is a private investment firm that invests in environmental opportunities, including companies, funds, and public-private partnerships in the renewable energy, water, and sustainable agriculture and waste-to-value sectors. Torrefaction is a biomass pretreatment process where raw green biomass is subjected to temperatures between 250 and 300 degrees Celsius in a near oxygen-free environment. During this time, the cellulose is volatilized, and the resulting solids exhibit completely different physical and chemical properties than the original biomass. During the process, nearly 100% of the moisture is eliminated, yet 80% of the energy content is preserved along with 70% of its dry weight mass. I know that this table is a bit busy, but if we go through it, you can see the differences between the different forms of wood. If we look at wood chips, white wood pellets, torrefied pellets, I put a column in here for steam exploded pellets. For those of you who are not aware, a company called Zilka has developed a pretreatment process based on steam explosion, and so I put that column in there. Charcoal and coal. I'm often asked the question, well, torrefied, I mean, that must be a lot like charcoal. Well, I think this table will explain to you where the similarities are and where the differences are. If we look at moisture content across the board here, each one of these has slightly different moisture contents. The highest being wood chips, wood pellets, 7 to 10%, torrefied pellets in 1 to 3% range, uh, steam exploded pellets, about the same as torrefied, maybe a little bit lower, charcoal, basically in the same range, and coal. It's hard to, coal has a moisture content that can really vary a lot, but 10 to 15% moisture is quite common. The heat content, the calorific value, as measured in megajoules per kilogram, wood chips are 9 to 12, wood pellets about 1.5 times that. Uh, Torrefied pellets over twice, can be twice the calorific value of wood chips, and 1.3 to 1.5 is times what whitewood pellets are. Steam exploded pellets, just a little bit less than that. Charcoal, of course, quite a bit higher. So this is one area where the charcoal is different than torrefied, and of course coal. Percent volatiles, uh, wood chips 70 to 75%, the same as whitewood pellets, because whitewood pellets simply take the chips and densify it into a pellet. They have not been chemically altered. Torrefied pellets have been thermally altered, and their volatility is lower. I cannot speak for steam exploded pellets. I do not know. Here's where we come up with our first really big difference between torrefaction and the manufacture of coal. Torrefaction results in 55 to 65% volatiles, where charcoal is much lower in the 10 to 12% range. This is a marked difference, and this is why if somebody asks me about, well, isn't torrefaction just the same as making charcoal? And no, I say it is not. And this is one of the reasons. There's another. And coal, of course, is in the 15 to 30%. Fixed carbon, 20 to 25% for wood chips, the same for whitewood pellets. Torrefied pellets are slightly higher than that. Charcoal, of course, is much higher on fixed carbons, 85 to 87%, and coal is 50 to 55%. Bulk density, as measured in kilograms per cubic meter, wood chips are of light density, only 200 to 250 kilograms per cubic meter. You'll notice wood pellets. This is the big advantage of whitewood pellets over wood chips, and this is why you see ships going to Europe in white wood pellet form and not necessarily in chip form, because you can put a lot more weight in a cubic meter in a ship hold. Torrefied pellets are even better than whitewood pellets because they have a higher bulk density of 750 to 850. Steam exploded, just in the same range. Charcoal, of course, is very light, as I'm sure we all know. And coal, if you look at torrefied pellets, steam exploded pellets, and coal, they're all in the same range. And finally, the volumetric energy density is as measured by how much energy can you put into a given volume. Wood chips are very low. If you make whitewood pellets out of the chips, you literally increase by a factor of 3. And if you make them into torrefied pellets, it's a factor of 5 to 6 better. Steam exploded pellets, not quite as good as torrefied pellets, but fairly close. And then charcoal is low from a volumetric energy point of view. And coal is, you will notice that torrefied pellets, steam exploded pellets, and coal is all relatively in the same range. The big advantage for torrefied biomass is that it's hydrophobic, it's brittle, and it's easily grindable. Those are physical characteristics that differ from either wood chips or whitewood pellets. If we just look at the issues inhibiting the use of wood pellets without any pre-treatment other than sizing. Wood chips are low in density and bulky. They're wet and highly wettable. They're very expensive to grind. You have trouble feeding them because of the non-uniformity in the particle size. They have low energy content on a weight basis, low energy density on a volume basis, and they're bioreactive, meaning that they will rot. Torrefaction solves all of these issues. Has a much higher bulk density. It's dry and hydrophobic, easily grindable. Uniformity allows ease of feeding. High energy content on a weight basis, high energy density on a volume basis, and it is not bioreactive. Torrefaction can be applied to all types of wood and grasses and other types of biomass, resulting in a uniform commodity type fuel. Let's take just a minute and talk about what's going on in the rest of the United States with regard to torrefaction. About 6 months ago, there was a consortium formed to address in detail and in a very timely, in a quick time frame, the issue of torrefaction. The founding members of this consortium of advanced wood to energy systems, it's called CAUSE, is the United States Forest Service through their Forest Products Laboratory, the Hertie Advanced Materials Development Center at Georgia Southern University, and the U.S. Endowment of Forestry and Community. These three groups are the founding members of CAUSE, and CAUSE will attempt to assess the challenges and knowledge gaps relevant to the advancement of torrefaction technology. They're going to put $4 million into this effort, and they're going to embark upon a 24-month work plan with an aim to validating torrefied wood as a promising renewable energy market solution. From their literature, you will see that torrefied wood has a significant market potential as a hydrophobic, densified energy carrier that stores, travels, and functions much like coal. We have attended, representatives Terra Green have attended the initial meeting of CAUSE. We hope to be working with them. ARB, the majority owner of Terra Green, is now a member of this consortium. Before we leave this subject, let me say that the reasoning behind, or the drivers behind this consortium, is that are that America's forests are a vital natural resource. They cover a third of our nation's land, and yet more than half of our forests, both public and private, are in decline. Forest conditions are driven by declining demand for our wood forest products, changing climatic conditions, endemic and exotic pests, diseases. The need for policies that support both cost-effective and environmentally desirable market solutions. A third of our nation's sawmills have gone away, and more than 40% of our pulp and paper mills have gone away since 1990. So the demand for forest products has declined. Deteriorating forest conditions have led to increasing size, intensity, and acreage of wildfires. The Forest Service spends more of its money on fighting forest fires than on any other single activity, costing more than $3 billion a year in federal tax dollars, and billions more in economic and environmental loss. They can clearly demonstrate that if forests receive treatment, if the fuels that are present in a forest are removed, the chances of catastrophic wildfire is significantly diminished. And they also recognize that coal-fired utilities in the U.S., which consume approximately 860 million tons per year of coal, could benefit greatly by the adoption of torrefied wood as a replacement or co-firing material. In part of the cause study, they will be looking at two different supply chain models. And I must admit a bias here because the two models, the first one is a distributive model where you take small torrefaction facilities and locate them very close to the source of the biomass in the small rural communities. So you build a lot of them and you put them right next to the biomass. Yes, you do suffer some loss of economy of scale, but you also enjoy much lower transportation cost because you're only transporting 40% of the original material that comes out of the forest. So the advantage is lower transportation cost and locating the units in right next to the biomass, but you do suffer some lower economies of scale. The other model is the centralized model, where you remove the material from the forest and transport it as wood chips to a central, much larger torrefaction facility. Now, the disadvantage is the higher transportation costs, but you do enjoy some economies of scale because the facility is so much larger. There will be situations when one model is better than the other, but the distributive model offers the most benefit to rural communities by keeping jobs in the local community. I believe that to be the better model in the longer run. In the fall of 2012, the managers at Terra Green Energy made the decision to build a small-scale commercial torrefaction process in Port Allegheny, Pennsylvania. It's in McKean County. There were three reasons why this decision was made. First, of course, to demonstrate the technology. Second, to provide large-size samples for testing. And three, to utilize this demonstration facility as a marketing platform. We can bring prospective customers for the technology and the product into the site, which we are happy to do, and show them a working torrefaction facility that a full commercial would look exactly like it, and in fact, the algorithms that control it, the computers that control it, are all the same as on a full-size commercial plant. The system consists of three thermally integrated subsystems: a rotary drum dryer, a combustion unit, and our own proprietary reactor. The system includes all the necessary material conveyance systems: hot gas, ductwork, dampers, airlocks, fans, and a complete instrumentation package to measure and manage the process. The gases emitted from the reactor are transferred to the combustion unit where they are oxidized, resulting in capturing the thermal energy from that oxidation and also allowing for very low emissions from the plant. The combustion unit provides the thermal energy for both the reactor and the pre-drying system. TGE's small-scale plant can produce about 1,000 pound an hour, about 12 ton a day in a continuous flow process. Here's just a very simple block diagram of our torrefaction process. See if I can. The raw green biomass is conveyed into the rotary drum dryer. You notice there's a small amount that also goes to the combustor. You will also see that at no point or in no place on this diagram do you see the use of fossil fuels. No fossil fuels are used at any point or at any time in the process. Everything, all the energy required, with the exception of electrical power, of course, to drive the motors and fans, but is derived from the raw green biomass. So it goes into the rotary drum dryer. It is dried to about 12 to 15% moisture. It goes into the top of our torrefaction reactor. It travels down through the torrefaction reactor. We have the ability to control the residence time in the reactor from as little as 12 minutes to as much as 45 minutes if we so desire. The material goes down through the torrefaction reactor, exits the bottom, goes through a quench unit and a screw conveyor cooler, and exits toward densification. You will notice that the combustion unit exchanges the gases with the torrefaction reactor, and the flue gas from the combustor goes up and provides the thermal energy required for drying, and then exits the process. In typical operation, the wood chip moisture content will going in right here. Going in it can be between 40 and 50%. The torrefied chip moisture content coming out, 1 to 3%. The torrefied chip yield on a wet basis, 40 to 45%. So what comes out here, for every pound that goes in, which is both biomass and water, only 40% comes out, given moisture contents in the 40 to 55% range. The torrefied chip yield on a dry basis is between 70 and 75%. Future Metrics, which does a lot of work on white wood pellets and black pellets, estimates that a torrefaction facility, including densification, will have a capital cost of approximately $255 times the facility's tons of annual capacity. Even though they're the Future Metrics made this estimate, we agree with it. We believe that it's very, very close to this number. So a torrefaction facility that has 100,000 ton per year of output capacity would cost around $25 million, give or take. I have some pictures of our small-scale commercial unit. The first, and this is not connected to the continuous flow process, but when wood chips are delivered to the site, we process them through a grinder, because the non-uniformity in the particle size is detrimental to the process. So we do grind them down some, not very far. It's not a fine grind by any means, but we do. This allows us to take low value feedstocks that have a high degree of variability in the particle size. First stage of the process involves the pre-drying through a rotary drum dryer. You can see in the picture. You can see in the picture that we have a bin here This is where the wood chips would be delivered into. They would then be processed through a rotary drum dryer down to between 12 and 15% moisture. If you were making a whitewood pellet, you would drive these moisture contents down to probably 8 to 10% moisture. We are not required to bring it down quite so far. This is a view of the other end of the rotary drum drying system. You will notice a cyclone separator, an ID fan, and various other equipment, including a shaker screener. I'm pointing to it now, and then it's difficult to see, but there's a metering bin downstream of the shaker screener. The shaker screener is in there to remove any. Oftentimes, the wood chips will have some dirt attached to it, and through the rotary drum drying process, the dirt will dislodge from the chip, and as it is dried, and it'll come over here onto the shaker screener and be ejected from the system. This is a view of the combustion unit. That's this unit right in here. You can also see that we have heat exchangers on the top of the unit and various ductwork that connects it to both the rotary drum dryer and the torrefaction reactor. This is the heart of the TGE torrefaction system. It is a vertical hearth design reactor. The material goes in the top and comes down through the reactor, exiting on bottom. It's hard to see. There's a quench unit right in here, and then the cooling screw for cooling the material. The entire torrefaction system is controlled by an operator in a computerized control room. You can see that the operator can set it as control panel using computer controls, and he can actually look through these viewing windows and see and keep an eye on the process outside. The entire system operates with 2 people, the operator managing the system and an outside person handling the material. So he's got an operator and a helper. Let's talk for just a moment on the International Energy Agency's 4th workshop on co-firing biomass with coal. It was held at the Nittany Lion Inn on the Penn State campus on November 5th and 6th. It was organized by the IAEA Clean Coal Conference, Clean Coal Center out of London, England. And countries represented included all those listed on the screen and others. It was very well attended, and it was a very interesting conference. And I have a few slides that show some of the things that were presented there. But what we were really excited about is the fact that just prior to the conference, we received a call from the International Energy Agency asking if we'd be willing to host a tour of our torrefaction facility by attendees at the conference. So on November 4th, we hosted an IEA tour at our site. You can see here the attendees arriving by coach at our site. There were 27 people representing countries from all over the world, and we broke them up into smaller groups and provided a tour guide for each group and showed them through our torrefaction facility. You can see this group here outside looking at the rotary drum drying process. This group here over by the where the fines are extracted from the dried stream into the reactor. And here you see a group with looking over the torrefaction reactor. Here are some additional pictures of that tour. Again, outside by the ID fans, inside again by the reactor. Here's a picture of the group by the combustion unit. And finally, this picture was taken out by the grinder where the material is prepared prior to torrefaction. We were very excited to do this. We had a chance to show off our technology and what we've done. I mean, everything we've done on this small-scale plant has been done to industry-type standards. I mean, my partners and I all come out of the conventional energy industry. We know what safety standards and construction standards are, and this facility has been built to those standards. And we're very proud and happy to show it off. This was I found this flame picture very interesting, as this is what coal and torrefied biomass looks like through a PC boiler flame. And this is the initial market envisioned for torrefied biomass. Coal-fired electrical generation facilities with pulverized coal boilers. And there's actually, in the last 12 months, here in North America, significant steps have been taken with co-firing. Not all of it with the torrefied, but some. And let me share some of that with you. Ontario Power Generation has converted their Atikokan generation station to whitewood pellets. They did this in 2014, 205 megawatts of capacity, new silos, burners, controls, and modified pulverizers. Again, this is a whitewood pellet. This is a whitewood pellet conversion. Whitewood pellet conversion. Now look at this one on the right-hand side of your screen. This is a conversion to biocoal pellets done at Thunder Bay Generation. This conversion is underway. It's 150 megawatts of capacity, one unit, and they're modifying their pulverizers. They're storing the material outside. Look at the difference in the cost. $170 million conversion cost, less than $5 million conversion cost. Now, given these biocoal pellets are steam exploded pellets, they went in that direction because biocoal pellets were available at this time. They could not get an adequate supply of torrefied pellets, so they went with the steam exploded pellets. That's, of course, one of the challenges. Here's another. This is a field test at a golf facility. This, I believe, is down in Florida. The participants in this was a co-firing field test by Southern Company, Alabama Power, Ontario Power, Gulf Power, and EPRI was involved. And here are the outcomes. Successfully fired up to 100% torrefied wood in the pulverized boiler. They set a Southern Company record for co-firing renewable energy. They found that by adding torrefied wood, reduced unburnt carbon losses. This is significant for them. And it also resulted in lower, greatly reduced emissions of NOx, SOx, and other emissions. In summary, torrefied wood, they found, was a relatively easy way to generate large quantities of renewable energy using existing power plants. And again, this is from the IAEA conference on co-firing. Here's what the scenario looks like today here in Pennsylvania and elsewhere in the United States and around the world. Uh, and it's pretty simple. You got coal miners, and you got electrical power generation facilities. And this is the way it's been for 100+ years. Uh, but things are changing for any number of reasons, which most of us are very aware of. Here's what tomorrow can look like if we so desire. You continue to burn some coal at 70 to 90%, but you also produce torrefied biomass from a combination of hybrid willow and other on-purpose grown energy crops, low-value forestry material. You convert it into, when it's torrefied, including grasses here, when they're torrefied, they all look the same, given they have slightly different chemical properties, which need to be taken into account. But this material, once it's torrefied, can be fed directly with coal into electrical power generation plants, and this scenario provides a tremendous market for on-grown energy crops and low-value forestry materials. How much does it cost to generate electrical power? I think we all are aware that installed hydro is the least expensive electric that we generate here in the United States. A PC coal-fired plant greater than 35 years with new emission control, 600 megawatt, can generate electricity for about between $36 and $37 per megawatt hour. Now, these are not my numbers. These numbers come from a couple of sources, a report, and they're listed at the bottom of the screen, a report for the Energy Information Agency in April of 2014, and also some information prepared for NREL by Black and Veatch back in February of 2012. So they looked at all the entire spectrum of electrical generation sources, and they put them on this continuum. You will see that natural gas combined cycle at about just over $55. Now, given that this is probably a little bit lower today because natural gas prices are a little lower, but because these new natural gas combined cycle plants cost, let's say $500 million to $750 million a piece, and you have to pay for that, they're probably not that much lower. You can see where nuclear is, land-based wind, offshore wind, solar PV. Now these are all changing a little bit as the technology improves. They're getting less expensive, but this is where these reports place them on the continuum. Now, what happens if you take a coal plant greater than 30? 2/3 of our fleet of coal-fired plants are greater than 35 years old, meaning that the initial cost has been depreciated, so that they're off the depreciation schedule, with the exception of the new emission controls, and the majority of these are PC. The technology is PC, pulverized coal. So what happens if we take this plant and burn and fire it with 10% torrefied biomass? You will see that the coal plant with 10% co-firing, which results in 60 megawatts of renewable energy, and the cost is about $5 more per megawatt hour, or a half a cent a kilowatt hour, a half a cent more, and still considerably less than natural gas combined cycle. If you increase that to 20% or 30%, you can see that it goes up about a half a cent per kilowatt hour with each 10% increase in co-firing rate. So this is very important information where we know if you were firing at 30% co-firing, you would be generating 180 megawatts of capacity at this one plant. So using existing facilities to generate this renewable energy is important, and being able to mitigate some of the emission issues of these plants by co-firing is also very important. Environmental benefits of co-firing, the testing in Europe and elsewhere, and there's more data supporting this literally on a week-by-week basis, that co-firing results in lower emissions of SOx, mercury, NOx, and of course CO2, because it's a renewable fuel. The synergies of co-firing have great value here with these plants. Here are the beneficiaries of torrefaction. Forestry landowners, both public and private. It gives them a new market. There's a benefit to agricultural landowners of marginal cropland. Having a large market for on-grown purpose energy crops is very important, and these agricultural landowners will benefit. It will benefit coal mine owners and miners and their families if we can keep some of these pulverized coal boilers facilities operating. It's a benefit to the owners and employees of the coal-fired electrical generation facilities. Oftentimes, these last beneficiaries are somehow forgotten, but it's a benefit to many rural communities across our nation. It puts jobs back in the rural communities, and this is important. I mean, I live in northwestern Pennsylvania. I see our greatest export up here is our children, and that's very sad. I really want to work to bring jobs back to the rural community. As a former public official, I also know that it's important that local governments preserve and enhance the tax base. I see this as a way that can happen. And finally, it's a major benefit to our country's electrical power consumers. Our nation is built on low-cost, affordable electrical power, and we cannot afford to give that away as we move into the future. Tremendous value for a wide range of stakeholders. In conclusion, co-firing in existing power plants with torrefied biomass is relatively fast. It can happen quickly. It's low cost, and it can generate very large volumes of renewable, sustainable, carbon-neutral power. There is an urgent need to engage all the various stakeholders potentially impacted by the benefits of co-firing. The opportunities are significant, and the tent is big. Stakeholders along the entire supply chain should consider becoming engaged in this effort. And then I'd like to ask, how can the new Bio consortium facilitate? How can new Bio help move this forward? And I just kind of leave that as a question out there. Finally, Terra Green Energy is working to identify like-minded strategic investors from among the various stakeholder groups who can see the tremendous opportunities offered by co-firing with torrefied biomass. And I'm excited about this presentation. I'm excited about the work that we do, and I want to thank you for today. Sarah?
Thanks, Tom. That was an excellent overview. I certainly learned a lot. Uh, Participants, please keep Tom's questions in mind as you generate your own questions and comments. Type them in the chat pod on the left side. We have a couple of questions already, so I'll just get started with those, and Tom, just jump in whenever you like. So the first, it's a clarification question on the order of events in the processing. So when you talk about the advantage of torrefied pellets being easy to grind, does that reference sort of downstream use for them in a co-firing situation, so grinding of the actual pellets, or the initial grinding in order to make the pellets before the processing is complete?
Oh, thank you for the question. It's about grinding in the mills at the co-firing location. Because torrefied biomass grinds in a very similar way as coal, and completely different than wood. So when I talk about that, it's about at the co-firing location, not in the manufacture of torrefied wood.
So in your experience, it's much easier to grind a torrefied pellet than a whitewood pellet or some of the other materials you mentioned?
Well, it's much easier to grind than a wood chip, and whitewood pellets have already been ground in their manufacture. So it's the harder comparison with whitewood pellets. Wood pellets are more volatile.
Okay, thanks. Other questions about the sourcing of material. So generally, if you could speak to how you're sourcing material for the demonstration plant in Pennsylvania now, what's the source of woody biomass you're using? And then after you kind of address that, have you ever experimented with non-wood materials, so herbaceous biomass sources in your processing?
Okay. At the demonstration site, we are working with a local sawmill that gives us has provided mill chips for us. So it's entirely wood. In our laboratory testing prior to building the demonstration plant, we have worked with grasses and other biomass, but in the demonstration plant, it's been exclusively wood up to this point.
Okay. In a scale-up situation, would you create similar partnerships with, you said, for example, a sawmill, or would you source using a different method for a larger base of material?
You would need to source differently when you went to a commercial plant, because no sawmill can give you the volume that you need. So you will need to put together a supply chain to provide adequate volumes of raw materials. 330 days of the year.
So to take a question that's in the left-hand side here, to scale that thought way up, can Pennsylvania grow and deliver enough biomass to supply enough torrefied material to replace even half of the coal used in PA? Or do you see this as a smaller scale dent in that?
I mean, Pennsylvania uses an awful lot of coal, and there is, we would probably be taxed here in Pennsylvania to do 10%, but we should if 10% is if we're able to do 10%, then we should do 10%. But half is not. I do not see enough biomass. Combination of forestry materials and on-grown energy crops would not approach 50%.
Okay, so let's take the 10% example here. Mike points out that consortiums like like the one you're already engaged in, as well as the new Bioconsortium, are really designed to help companies like yours, especially on sourcing large-scale amounts of feedstock. So with the idea of 10% being pretty easy to implement in a lot of coal operations, and with so many coal plants in the state and in the area, he asks, why haven't any bitten yet?
Oh, that's a very good question. But as I said a couple times during my presentation, there's a lot of things have changed over the last 12 months as more of this testing is being done. But to be honest with you, when it comes right down to it, the electrical power generation, the owners of these plants have to be motivated to include torrefied biomass. Whether they can are required to do that because of carbon emission requirements or other emission requirements. There's got to be a motivation for them to do that, and I don't think we've explained the benefits to them adequately yet.
So do you see a mandate as being necessary, or would some other kind of incentive, a tax incentive or something like that, be strong enough, do you think, as motivation?
I believe that the EPA's requirements for lowering the carbon density of the electrical power that we currently generate will play a part. But they have to see some economic advantage, and that economic advantage could include saving a valuable asset. There are quite a few plants in Pennsylvania, power plants in Pennsylvania, currently scheduled for shutdown. Companies are walking away from very valuable assets. If torrefaction and co-firing could extend the life of an existing power plant, there is quite a bit of value in that, and it doesn't require a government mandate to do it.
Yeah, and to your point earlier, if a distributed model is the preferred model, then it gives certainly a lot more flexibility in terms of where those processing facilities can be sited to prioritize areas like that. Would you agree?
I would agree.
Okay, we have a couple questions about physical properties and just general characteristics of the material. So the first question is what is the cost of torrefied pellets per ton that you would sell them for, or maybe the cost of actual processing?
Okay. Well, the majority cost of torrefied pellets is the raw material cost. If you do sensitivities around it, the cost of the raw material is always the major cost driver. But we see the cost of a torrefied pellet commercially, as commercial plants are built, probably in around the $9 per million BTU range. Of course, that's quite a bit higher than natural gas now, but that's about where it's going to where it would be right now. If you were going out to buy a ton or 5 ton or 50 ton of torrefied biomass today, of course it would be quite a bit more than that. But going forward, when they're commercial, I would guess somewhere in the neighborhood of $8.50 to $9 per million BTU.
For the processing step itself.
Well, that would be the finished product cost. Mm-hmm. That would be the finished product cost.
So the added cost of the actual torrefaction process, you would consider that equal or more, even recouped in the savings in terms of storage at a later downstream facility?
Well, that's one of the benefits. I mean, one of the benefits, it can be stored outside on the ground. It doesn't need to be stored in covered buildings. It can be handled and treated just like coal is treated. But that's one of the benefits the customer gets to to save.
Can you explain either the process or just the basic descriptive characteristics differences between a torrefied pellet and a steam exploded pellet, and how they're used in downstream markets?
Well, that's a little bit more difficult question because
Okay.
I do not know too much about steam exploded pellets, other than to say both torrefied and steam exploded are hydrophobic. They can be stored outside. They don't need any special handling characteristics. Uh, Steam exploded have a lower heat content, uh, slightly than torrefied. Torrefied having more energy, uh, but other than that, they're very similar.
Okay, thanks. We have one more question asking about how the pellets themselves hold together. Is there a binder used? Is it just the reconstitution of lignin? How is that achieved?
Very, very good question. And let me answer it this way. If you go back in the literature several years, they were predicting that torrefied wood would be very easy to pelletize because the lignin would be, you could heat the material and the lignin and it would and the pellet would stay together. Companies that are working in torrefaction have found that not to be true. In fact, making a good pellet is more difficult than making a whitewood pellet. People are doing it, and they're doing it without binder, but it takes a special set of conditions to make a good pellet without a binder. And making it without a binder is very important because if you start adding a binder, you're starting to add significant cost to it. So yes, companies are making good pellets without binders, and to be honest with you, companies are holding that pretty close to the chest right now.
Yeah, understandably so. Do you know of any coal plants that are currently using either torrefied wood or torrefied grass in co-firing? How extensive would you say that practice is?
It's not. I mean, we're seeing some tests that I showed you down in Florida. There is a group out of Quebec, Canada, right now that's out with proposals for supply of torrefied wood so that they can do a large test fire, and we will be responding to that request for proposal. But I know of no plants today that are continuously firing or co-firing with torrefied. But if you give it another year, give it another couple of years, and you will be seeing it.
So you mentioned, your question of how consortiums can facilitate the goals of your company, and it seems like the role of a consortium, be it New Bio or the other one that you mentioned that you're engaged in, probably the most significant role that a consortium could take would be to try to connect stakeholders that on a broader scale with more diverse interests maybe than you might be exposed to. It seems like the conference that you attended and others like it would be a great opportunity to do that, and hopefully you can stay engaged with those consortia and continue to pursue those goals with a variety of stakeholders in mind. It seems like you've done a great job of pursuing that so far. We all very much appreciate the information you've given today. If there are any last minute questions, feel free to type them in. But in the meantime, Tom, do you have any concluding remarks?
I would just ask those who can hear my voice now. One of the most difficult things that we come up against is getting audiences with the owners, operators of power plants, so that we can go in and talk to them about torrefaction. And if there's anybody that could facilitate a meeting for us so that we could present the advantages of torrefaction, we would very much appreciate it.
All right, we'll keep that in mind. For our participants today, you can see Tom's contact information at the bottom of this slide, so feel free to take it down and contact him or anyone at New Bio for further questions and information.